Jai Hind students, welcome to my YouTube channel. Students, always remember, every single day is a good day. Every single day is a blessed day. No matter how bright or dark it is, because every day gives us or it provides us an opportunity. So students, we need to have that positive approach towards life. It's our attitude which can make a day from fear to good, from good to better, and from better to best. Right? So with that students, let's begin today's session. Today we are going to derive a very important expression. We need to derive an expression for the torque experienced by a current carrying coil under the influence of uniform magnetic field. Right? So in the previous session, we have discussed about the magnetic force experienced by a current carrying conductor under the influence of magnetic field. So we are aware, whenever a current carrying conductor is under the influence of magnetic field, then it experiences a magnetic force which is given by F vector. It is equal to IL vector, it is the current element, cross B vector. This is the cross or the vector product. This formula we have derived in the previous session, right? This is the expression for the magnetic force which we will be using today so as to obtain an expression for the torque experienced by a current carrying coil under the influence of uniform magnetic field. So students, for a current carrying coil here, I have considered a rectangular coil ABCD. This is a rectangular coil under consideration. Let AB is equal to CD with the length of the rectangular coil, and let us represent it by L. This AB and CD, this represents the length of the rectangular coil under consideration. And the width, that is the breadth, may be considered to be, let AD is equal to BC is equal to B. So the breadth of this rectangular coil is considered to be small letter b. And students, this is the axis. This is the axis actually. This is the axis of the coil. So this is a rectangular coil A, B, C, D. Right? There is a rectangular coil. Suppose the current is flowing along this direction. This is the direction of the flow of current in the anti-clockwise, right? This is the direction of the flow of current from A, B, C, D, that is in the anti-clockwise direction. And students, this current carrying coil is under the influence of uniform magnetic field. It's been represented by a set of parallel lines indicating the magnetic field in the given region is uniform, right? So it has been drawn by a set of parallel lines directed from left to right. And students, this one, this dotted one, that's the normal to the plane of the coil. This is N1 and this is N2. This is the normal to the plane of the coil. Normal to the plane of the coil means if this is the plane of the coil, then perpendicular to the plane of the coil is known as the normal to the plane of the coil. So again I repeat students, I have considered a rectangular current carrying coil A, B, C, D whose dimensions are L and B. And I have considered I be the current flowing through this rectangular coil in the anti-clockwise direction. Right? N1, N2 are the normals to the plane of the coil. And this current carrying coil is under the influence of uniform magnetic field directed from left to right, represented by these set of parallel lines. Clear students? Okay. Also let this be angle theta. So theta, as you can notice, it is the angle which the normal to the plane of the coil makes with the direction of the magnetic field. Clear students? So theta, I must mention over here, theta is the angle between the magnetic field. It is the angle between the magnetic field B and the normal to the plane of the coil. and the normal to the plane of the coil. Right? So, theta is this angle. This is the normal to the plane of the coil N1, N2, and this is the magnetic field. So, theta is the angle which the normal to the plane of the coil makes with the direction of the magnetic field. Right? And this may be considered to be alpha. This may be considered to be alpha. This angle, this small angle, it may be considered to be alpha. So, alpha, students, is the angle which the magnetic field makes with the plane of the coil. Alpha is the angle between the magnetic field and the plane of the coil right? So do remember these points. Theta is the angle which the magnetic field makes with the normal to the plane of the coil, and alpha is the angle which the plane of the coil makes with the direction of the magnetic field. So students, what's the relationship with theta and alpha? This is the normal. So obviously, the angle between these two must be also 90 degree, isn't it? This angle must be 90 degree. So what's the relationship between theta and alpha then? Theta plus alpha must be equal to 90 degree. So we can represent torque both in terms of theta as well as in terms of alpha. Again I repeat, students, there shouldn't be any confusion between theta and alpha. Theta is the angle which the direction of the magnetic field makes with the normal to the plane of the coil, and alpha is the angle which the direction of the magnetic field makes with the plane of the coil. And what is the relationship between theta and alpha? The sum of theta and alpha is equal to 90 degree. Clear? Okay, let's proceed then. So let us consider the arm AD. Let us consider arm AD, or rather DA, right? DA, right? Along the direction of the current. Let us consider the current carrying arm DA. Let us consider this arm to be experiencing force F1. This current carrying arm is under the influence of this magnetic field. Therefore, obviously it will experience a magnetic force. So that magnetic force is represented by F1. It will be equal to, as per this formula, current flowing through this arm is I. Length, it is to be measured along the direction of the flow of current. So that current multiplied by that length becomes current element. It is then that it will be treated as a vector quantity. So I and length will be measured from D to A. So this entire term becomes current element cross B vector. Am I clear, students? Okay, now let's consider the angle between them. So magnitude, it would be equal to I. The magnitude of DA, it's equal to B. Capital B. Sine, this is the cross product, right? What's the angle between this current element and the magnetic field? Now look, this at this point, this is the current element. I vector, dA vector. It is from D to A along this direction. And this is the magnetic field. This is the current element and this is the direction of the magnetic field. So, this is the angle between IDA vector and D vector. Right, students? I've always maintained the angle between the two vectors should be such that from a given point, either both the vectors should emanate, that is the tail of two vectors should coincide, or the head of the two vectors should coincide. Then that will be the effective angle between the two given vectors, right? So, in case we need to find out the angle between IDA and D vector, this is IDA vector at this point. Suppose this is point X. At point X, IDA vector is along this direction and D vector is along this direction. So, this is the point where both the vectors are originating, isn't it? So, this will be the angle between IDA vector and D vector. And what is this angle? This is 90 degree and this is theta. So, what will be the angle between these two? It will be 90 plus theta. And we are aware, students, sin 90 plus theta is cos theta. So, the magnitude of F1 is BI B cos theta. Isn't it? Put this as equation number 1. This is the magnitude. Now what about the direction? The direction of the cross product of the two vectors is given by right hand thumb rule, isn't it? The fingers should curl along the direction of orientation of the angle. Here the angle is to be measured from idea vector to B vector. So it is directed like this, right? Idea vector to B vector. It's oriented along this direction. Idea vector and this is B vector. So idea vector to B vector along this direction. So students, using this rule, the thumb will give us the direction of the vector product of idea vector and B vector. So the direction of F1 would be along the axis and in the upward direction. This is F1 vector. Clear, students? Here the angle between idea vector and B vector is not 90 degree. Therefore, we cannot make use of Fleming's left hand rule. That is applicable when the angle between those two is 90 degree, isn't it? So here we can make use of right hand thumb rule so as to get the direction of the resultant of the cross product of these two vectors. So its direction is along the axis and upwards. Okay, students. Now consider this arm, the opposite arm. Now let us consider arm BC. Suppose this current carrying arm under this influence of magnetic field experiences force F2. So in vector form it will be given by I, BC. This will be the current element entire term. The length is to measure from B to C. So this entire term will act as current element cross B vector. So this is the cross product. So its magnitude would be given by I, the magnitude of BC, that's the breadth of the rectangular coil B sine angle between these two. Now over here again the same concept. This is BC, IBC, and this is B vector. So this is the angle between them, this one. So the angle, suppose this is point Y, angle at point Y between IBC vector and B vector is alpha, right? And alpha is theta minus pi by 2. So it will be theta minus, or rather pi by 2 minus theta, isn't it? So it will be pi by 2 minus theta. Again I repeat, students, here we are supposed to get the angle between IBC and B vector. This is IBC. This is the current element. It is to be measured along the direction of the flow of current. This is IBC and this is the magnetic field. So the angle is alpha, and alpha is pi by 2 minus theta. So what do we get? We will get BIB cos theta. Put this as equation number 2. This is the magnitude of F2. Now what about its direction? Again, the resultant direction of the cross product of these two vectors can be found by using right hand thumb rule, isn't it? The angle is oriented from IBC vector to B vector. This is IBC vector and this is B vector, right? So angle is oriented from IBC to B vector like this. So in this case, the thumb is pointing along the axis and in the downward direction. So students, this will be the direction of F2. This is the direction of F2. So F2 is directed along the axis and downwards. Isn't it? Now observe these two. From 1 and 2, what do you conclude? These two forces, F1 and F2, both are of equal magnitude, each being equal to BIB cos theta. But they are oppositely directed. And they are acting on the same line. Their line of action is same. So whenever the two forces are of equal magnitude, acting in opposite direction and having the same line of action, then they tend to nullify or cancel out the effect of each other, right? So these two forces, F1 and F2, will cancel out or nullify the effect of each other, right? So no contribution of F1 and F2 towards the torque. So F1 and F2 both are of equal magnitude and being oppositely directed, they tend to cancel out the effect of each other, and both of them are acting along the same line but in the opposite direction. That is the reason why they tend to cancel out the effect of each other, right? So these two arms are left, AB and CD. Now consider third case. Consider arm, let us consider the arm AB. Let's consider this current carrying arm. And let us consider this current carrying arm AB to be experiencing force F3. So again, by using the basic formula, F3 vector, it will be given by current, and AB, the length is to be measured along the direction of the flow of current. It is only then that this entire term will act as current element, cross B vector, right? So here, what's the angle between IAB, that is the current element, and magnetic field? It is obviously 90 degree. So, in magnitude F3, it will be equal to I. Magnitude of AB is L, B, and angle between these two is 90 degree. Sin 90 is 1, so F3 it will be equal to BIL. Isn't it, students? Now, what about the direction? It can be found by using Fleming's left-hand rule. Why this rule? Because the angle between these two is 90 degree. Here also you can make use of thumb rule, but Fleming's left-hand rule is preferable. Anyway, it's up to you. So this is F, this is B, this is I, isn't it? This is the magnetic field, central finger is the current. Students, you must remember F, B, I, isn't it? Force, F force, B magnetic field, I is the current. Now look, magnetic field is directed from left to right. Current is in the downward direction like this. So thumb is indicating in the outward direction, right? So it is directed outwards. F3 is directed outwards. It will be represented like this, F3 vector. Outward, so let us represent by this symbol, directed outwards. So it is perpendicular to both B vector as well as it is perpendicular to IAB vector. All the three are mutually perpendicular to each other, right? Now, last arm is left. Consider the fourth arm of the rectangular coil, that is CD. So consider this arm of the rectangular coil. Let the arm CD experiences magnetic force F4. It will be given by I, CD vector, cross B vector. So again, students, angle between ICD vector and B vector obviously is 90 degree, isn't it? So what we get is, this is the cross product. So sin 90 naturally will become 1. So it will be equal to I, magnitude of CD is L, length of the coil, B sin 90. Sin 90 is 1, so in magnitude F4 would be equal to BIL. Right, students? What about its direction then? Again, let's make use of Fleming's left-hand rule, isn't it? This is the rule FBI. This is the magnetic field directed from left to right. This is the current. Current is from C to D in the upward direction, so it will be like this. Central finger will represent the current. So thumb in this case, which indicates the direction of the force, is directed inwards, right? F4 is directed inwards. So if I represent this as the outward direction, then inward direction will be represented like this. This is F4 and directed inwards. All the three are mutually perpendicular to each other, right? So students, the direction is inwards. Now concentrate on these two equations, third and fourth. No doubt, F3 and F4 are also equal in magnitude. They are also opposite directed, one in the outward direction, F4 in the inward direction. But students, the most important point to remember is F3 and F4 are not acting along the same line. Actually, they have different lines of action. Look, F3, it is acting along this line. And F4, it is acting along this line. So these two forces, although they are equal in magnitude, oppositely directed, but due to the fact that they are acting on different lines, they have different lines of action, therefore they won't cancel out the effect of each other. Instead, they will constitute a torque, as a result of which these two forces will constitute a torque and will induce a rotational effect. That is, it will make the coil, current carrying coil, to rotate in a particular direction about its axis. Understood, students? Look, this is suppose the coil, right? One force is acting in the outward direction, the other force is acting in the inward direction. So obviously, these two forces will constitute torque and it will make the coil to rotate about its axis in the anti-clockwise direction, like this, in the anti-clockwise direction, right? So, this is the direction, that is the anti-clockwise, in which the coil, current carrying coil, will tend to rotate about its axis under the influence of the torque due to the forces F3 and F4, right? So, our objective is to find out the expression for that torque, right? Okay, let's do it. So, students, F3, F4 being equal in magnitude, oppositely directed and having different lines of action will constitute a torque which will make the current carrying coil to rotate about its axis, in this case in the anti-clockwise direction as shown in the figure, right? And students, you are aware, the magnitude of the torque, it is given by, what's the formula? Magnitude of either of the force, magnitude of F3 or F4 multiplied by the perpendicular distance between them. This is the formula for the torque which we are aware of. Now, in order to find out the perpendicular distance between the line of action of these two forces, we need to concentrate on other diagram, right? We need to draw a diagram which will appear from the top view, right? If we look this coil from the top, then this is the relevant diagram. This is the diagram from the top view, like this. This is A, this is B. This is the top view of that particular diagram, right? Okay. This is the normal, which I have denoted by N1. This is N1, right? This is the normal, means it will make an angle of 90 degrees. This is the direction of the magnetic field, like this. This is the direction of the magnetic field. This is the direction of the magnetic field. And this angle is theta. This angle is alpha. And we are aware, theta plus alpha is equal to 90 degrees. No doubt regarding this, isn't it? Now students, AB arm, it experiences a force in the outward direction. So from the top view, F3 will be seen to be acting along this direction. And on the arm CD, F4 force acts and it is directed inwards. So it will appear to be acting along this direction. So this is the top view. So line of action of F3 would be this one and line of action of F4 would be this line. So these are two anti-parallel, right? They are having different lines of action. So students, we need to find out the perpendicular distance between these two. Suppose this is C. So CD, this D would be the perpendicular distance between F3 and F4. Clear students? So obviously it is the perpendicular distance, this is 90 degrees. Now this is alpha. So students, this angle would be also equal to alpha. Alternate interior angles, isn't it? This is 90, this is alpha. And since theta plus alpha equals to 90 degrees, so this must be theta. So since this is alpha, this is 90, the third angle must be theta, because the sum of the three angles of a triangle must be 180 degrees, isn't it? It is satisfying that condition. This is 90 and theta plus alpha is 90. Clear students? Okay. Now in this right angle triangle, consider sine theta. Sine theta is perpendicular by hypotenuse, that is CD divided by AB, isn't it? Therefore students, CD, which is the perpendicular distance between F3 and F4, it is equal to AD sine theta. That is, the perpendicular distance between F3 and F4 actually is given by AD. AD is AB is the breadth of the rectangular coil, which is considered to be B. B is the breadth and this is the length, isn't it? So AD represents the breadth of the rectangular coil. So D equals to B sine theta. Understood, students? Okay. Let's substitute this value over here. Therefore, torque is equal to magnitude of F3 or F4. F3 and F4, just now we have discussed, its magnitude is BIL, isn't it? So its magnitude is BIL. And perpendicular distance between them, that is D, which is equal to B sine theta. So therefore, torque is equal to BIA sine theta. Here, students, A is the area of the rectangular coil under consideration, and the area of the rectangular coil is length into breadth. So this is length, this is breadth. So length into breadth, that will give us the area of the rectangular coil under consideration. So capital A stands for the area of the coil. Moreover, students, if we consider this rectangular frame to be containing n identical turns, right? This is a rectangular frame over which n turns of conducting wire is wound over it. N turns. So for n turns, and students, in each of the turns, the current will be flowing in the same anti-clockwise direction. So each loop will experience this torque, isn't it? Therefore, for n turns, the net torque will be n times the torque experienced by a single turn. So for n turns, the torque will be given by n B I A sine theta. So this is the expression. Right, students? Also, it can be further rearranged or modified. We are aware, students, we have done in the previous section, every or each current carrying coil behaves as a magnetic dipole. One face of the pole, one face of the current carrying loop behaves as the south pole, while the other face of the current carrying loop behaves as the north pole. So every current carrying loop behaves as a magnetic dipole, and therefore current carrying loop possesses magnetic moment, and that magnetic moment is represented by M. M stands for, suppose, magnetic dipole moment, or simply magnetic moment. And in the case of a current carrying loop, magnetic moment is given by ampere turns, which is the number of turns multiplied by the current flowing through each of the turn. This is known as ampere turns into area of the loop under consideration. This again we have done in the previous session, right? So magnetic moment of a current carrying loop is given by ampere turns multiplied by the area of the loop, here NIA. So in place of NIA we can replace it by M. So therefore torque is equal to MB sine theta. So students, this is the magnitude of the torque experienced by this rectangular current carrying coil under the influence of uniform magnetic field B in terms of the magnetic moment. M is the magnetic moment, B is the strength of the magnetic field. Theta, students, it's actually the angle between the magnetic moment and the magnetic field vector. We'll discuss it with the help of a diagram. Right, students? Okay, students. Now let us try to represent the expression for the torque in terms of the vector form. Right? So torque, as we have discussed, in magnitude it is given by MB sine theta, right? MB sine theta. M is the magnetic moment of the current carrying loop under consideration, and B is the strength of the magnetic field, and theta is the angle between M vector and B vector. That I will convince you with the help of a diagram, right? Okay, students. In the vector form, we can write torque as M vector cross B vector. This is the cross product, and you are aware, students, the cross product of two vectors is always a vector quantity. So torque obviously is a vector quantity. Actually, it is an axial vector which is directed along the axis. So by using the properties of the vector product, tau vector must be perpendicular to both m vector as well as it must be perpendicular to b vector. Right? Now regarding the direction of the torque, I'll explain. Let's concentrate on that particular diagram again. This is the rectangular coil which we have considered A, B, C and D. Current is assumed to be flowing in the anti-clockwise direction, isn't it? This is the current. And students, this is the axis. This is the axis of the coil. Now, since current is flowing in the anti-clockwise direction, so this face of this coil will behave as the north pole, while the other face will behave as the south pole. Students, remember, we have already discussed it. The face of the loop through which the current appears to be flowing in the anti-clockwise direction, that behaves as the north pole, while the other face of the loop through which current appears to be flowing in the clockwise direction, that will behave as the south pole. So that is the reason why a current carrying loop does behave as a magnetic dipole, possessing two equal and opposite poles, north and south. And students, the direction of the magnetic moment is from south to north. This also we are aware. So magnetic moment, its direction is from south to north. So its direction would be from south to north, towards south and away from the north, right? So it will be like this, along the normal. This is the direction of magnetic moment. It will be along the normal, isn't it? It will be along the direction of N1. So this face of the current carrying loop behaving as a north pole, the direction of the magnetic moment would be perpendicular to the plane of the loop and directed outwards. In case the current is assumed to be flowing in the clockwise direction, then this face of the loop would have behaved as a south pole. In such a scenario, the magnetic moment would have been directed perpendicular to the plane of the loop and directed inwards. In this case, it is perpendicular to the plane and directed outwards, right? And this is the direction of the magnetic field. This is the direction of the magnetic field, right? This is the uniform magnetic field under the influence of which this current carrying rectangular coil is placed. Now M cross B. So the angle theta is to be measured from M vector to B vector, like this. M vector to B vector. This is theta. Look, this is theta. This is the normal N1. The direction of magnetic moment is perpendicular to the plane of the coil, that is along the normal, isn't it? And this is magnetic field. So theta is the angle between M vector and B vector, right? And theta, it is to be measured along this orientation from M vector to B vector. This is the orientation. This is the orientation. M to B. So M cross B. Let's find its direction. So the fingers of my right hand must curl along the direction of orientation of the angle, isn't it? The angle is oriented in the anti-clockwise direction, like this, M to B, like this. So the thumb is pointing in the upward direction. So torque will be along this direction. As I told you, torque is an axial vector. It must act along the axis. So it is perpendicular to both B vector as well as it is perpendicular to M vector, right? So this is the direction basically. This is torque. This is B vector and this is M vector. All are mutually perpendicular, and actually tau is perpendicular to both M vector as well as tau is perpendicular to B vector, and the angle between M and B is theta, oriented from M vector to B vector. I hope students this diagram is convincing and you are able to get the concepts clear, right? So this is the master formula. Tau in magnitude, it's given by mb sine theta. M is the magnetic moment of the current carrying coil, which is equal to the product of the ampere turns and the area of the loop under consideration, right? And in the vector form, tau is given by m vector cross b vector. It is perpendicular to both m vector as well as b vector and always acts along the axis. Torque is an example of an axial vector, right? Now let's concentrate on some special cases. Special cases. Let's consider case 1. If theta is equal to 0 degree or theta is equal to 180 degree, that is sine 0 is 0 and sine 180 degree is also 0, and tau, students, its magnitude is mb sine theta. So in both the cases tau would be equal to 0. Clear, students? So if the angle between the magnetic moment and the magnetic field is 0 degree or 180 degree, in both the cases the current carrying coil won't experience any torque. So what will be the situation like? It is this situation, like this. Suppose the current is flowing in the anti-clockwise, right? This is the axis, this is the normal. So this is the magnetic moment and this is the magnetic field. This is the normal. So what's the angle between these two, magnetic moment and magnetic field? It is 0 degree. So in case magnetic field is in a direction perpendicular to the plane of the coil, magnetic field is in a direction perpendicular to the plane of the coil, then no torque will be experienced by the current carrying coil. Clear, students? So whether the current in the coil is flowing in the anti-clockwise or clockwise, it doesn't matter. In case of anti-clockwise, it will behave as north. In case of clockwise direction, the magnetic moment will be directed inwards perpendicular to the plane of the coil. So whether the current in the coil is flowing in the clockwise or anti-clockwise, it is immaterial, right? If the magnetic field is perpendicular to the plane of the coil, then the current carrying coil will not experience any torque. So that's the conclusion. Okay. Case 2. Maximum torque. Now the value of tau would be maximum when the value of sine theta is maximum. So tau is equal to tau max when theta is equal to 90 degree, and tau max would be equal to mb sine 90 is 1. So expression for the maximum torque is m into b. M is the magnetic moment, b is the strength of the magnetic field. And this is the situation when the magnetic field lies along the plane of the coil. In that case, it will experience maximum torque. So what will be the diagram like in this case? This is the coil, suppose. This is the axis. So this is the magnetic moment, isn't it? In case the current is flowing in the anti-clockwise, then this phase will act as the north pole and magnetic moment would be perpendicular to the plane and in the outward direction. Suppose the magnetic field is along this direction, along the plane of the coil. That is, here theta is 90 degree. This is the angle, 90 degree. So this is the case where the current carrying coil will experience maximum torque. So students, what's the condition for the current carrying coil to experience maximum torque then? Yes, the magnetic field should be always directed along the plane of the coil. It is then the torque experienced by the current carrying coil will be maximum. Clear, students? And one more important point, very important point, students. I mean, here, just for convenience, we have considered the current carrying coil to be of rectangular shape, isn't it? We have proved this expression for torque for rectangular current carrying coil. But whatever be the shape of the coil, be it a circular or any irregular shape, suppose this is a circular current carrying coil. In this case also, the expression for tau is equal to m vector cross b vector will hold valid. The only thing is that in this case, the area of the coil would be considered to be pi r square. If the area of the rectangular coil is length into breadth. In case we consider the frame to be circular, then area of the coil would be obviously pi r square, where r would be the radius of the circular frame under consideration. Right? The same formula will hold valid. Actually, we can consider this to be divided into many rectangular frames like this. So for each and every rectangular frame, the expression for the torque would be same. So it can be easily generalized that for any shape of current carrying coil, the expression for the torque will remain same. It is valid for any symmetrical loop or symmetrical coil or any irregular shaped coil, right? So this was an expression which is very important from the coming topics point of view. Clear, students? So I hope you have enjoyed this session, you have understood each and every concept. So that's it for this particular lecture. In the next lecture, we'll be discussing some numericals based on it, and also we'll be discussing a very important device, that is moving coil galvanometer, whose working is based on this principle. Right? So do join me in my next lecture. Till then, do take very good care of yourself and stay blessed always. Thank you.